All right, good afternoon. So, we will be continuing our journey talking about processes today, and especially how you manage processes. So, now we have multiple processes potentially, and right now we just kind of run them. They do whatever they want. They have that parent-child relationship, but we don't actually know how to use it or how to do anything useful with it. So just some more notes just to make it clear. So processes are assigned a process ID. Oh, yeah. Oh, screen again. Okay, sorry. So processes, when they're created, are assigned a process ID, otherwise called a PID, or it's just an integer if you want to think of it that way, whenever they're created, and then it does not change from that point forward. So as soon as you create a process through something like fork, well, fork is the only thing you can do, it gets assigned a process ID when it's created. That is a copy of whoever created it, and that's the only time it gets assigned a new process ID. And it doesn't change throughout its whole execution, and it's unique for every single active process. So on most Linux systems, like older systems, the limit is 32,000, and 0 is reserved as being invalid, and 1 is kind of that special process, that init process that gets created. So eventually, the kernel will recycle a PID after a process dies for a new process. So say if you have process ID 2 that exited, and that no longer represents an active process, well, if you run out of process IDs, then the kernel would use 2 for a new process, assuming that 2 is already dead. So the limit for this on like 64-bit machines is something like 4 million or something like that, but so the limits might vary and you can change them if you want. But just remember that each process has its own address space or independent view of memory, and we can accomplish this through virtual memory because each process thinks it has the entire memory space, and that's how the OS can actually make that illusion we saw before, where the same variable in 2 different processes had the same address, and one changing it in one didn't affect the other. It's because each process has its own address space, so its own view of memory. So if you change something on one, you don't change it on the other. So this is kind of bringing that state diagram back into it. This is how something like Firefox would create a process, or how we create a process with a fork. Eventually, you're going to launch your browser through some means, and it's going to be created, get a process ID like 1337, and then it would be in this created state where the kernel would have to load it into memory, load all the instructions, all that static information into memory, maybe set aside some virtual memory for things it requests, like other variables and so on. And then it would go ahead, as soon as it's created, it would go into this waiting state where it hasn't executed a single instruction now. It's just able to execute instructions. So it's loaded, its process ID or its virtual CPU is pointed at its entry, its start instruction, and it's just waiting for the kernel to actually schedule it and actually run the instructions that are part of that program. So eventually, the OS is going to say, hey, Firefox, you can run. It would do that context switch and change it to running, and it would go get the CPU, run some code. One of the things, if you're running it, you might click on, you might open a new tab, which would cause Firefox to fork, because part of the architecture of Firefox is every tab is its own process, and that way, we now know each process is independent. So that means each Firefox tab, just building off processes, are also independent. So that's a nice thing, that if you crash a tab on Firefox, or Chrome has the same architecture, it won't crash the rest of your browser. Because the old architecture was, okay, you open a tab, it's in the same process. So if you have, everyone has like hundreds of tabs open at a time, if one of those crashes and your whole browser crashes, that'd be pretty bad. But if every tab has its own process and one tab crashes, well, you're all good, because your main one can just say, hey, that tab crashed, just reload it, do whatever you need to do. So as part of running, Firefox would call fork, and then fork would go ahead, and then as part of that, you'd get a system call. So the kernel has to actually do all the tasks associated with that. So it would throw that Firefox process into the waiting state where it's ready to run, but we're doing a system call, so we're going to just sit it there because we're going to create a new process. And then a new process would pop up. Boom, our Firefox tab. It would get something like process ID 1338 or whatever the next available one is, and its parent would be whoever called fork on it. So in this case, it's parent or ppid or parent process ID is our original 1337, and then it would go through the same process. So it's in this created state, but most of the created state, instead of loading some stuff and initializing it, it will copy whatever forked it. So copy exactly where that is, exactly what it was doing, and which is this fork call, and copy all of its contents of memory, all of its open files, everything like that. And then it would be set in the waiting queue again, and this would be as part of the return for fork. So after this, they're both waiting, and the only difference between them at this point, they're exact clones of each other except for this relationship, and now as part of the system called the return value of that fork. So in the browser, the return value of fork would be like 1338, and in this newly created tab here, the return value of fork would just be 0 because it's the child. So then at some point, the CPU is going to choose maybe the main browser to run, maybe the tab. At this point, you don't know. It's up to the kernel to decide what to run, and we'll get into that later, how you make that decision. But for argument's sake, for you programming and argue about your correctness, you have to assume either of them could run at this point. So Firefox goes ahead, runs for a while. The CPU would want a context switch, run something else, so it gets stuck in that waiting queue again. Then maybe the tab runs for a little bit. It runs, executes some instructions. Then then the OS takes back control and says, oh, okay, I need to run something else now. Maybe the browser runs a bit more. Then it gets thrown back. Then maybe the tab runs a bit more, and then maybe it calls something like exit. And then if it calls exit, it goes into this terminated state, and it's actually still around. And we'll see how to actually delete a process today. So it just goes into this terminated state where it can't run anymore. It's done executing. It can't execute one more instruction, but all the memory associated with this process is still sticking around, and you can't actually delete that whole process from existence yet. What you have to do in order to delete them is do like some type of process communication. So the rule in Unix and all kind of Linuxy, Unixy operating systems is in order to clean up a process and all its resources, the parent has to acknowledge that it has terminated. So only when you acknowledge that process has terminated can you actually delete everything associated with it, including its process ID, and then go ahead and clean up. So it would have to do something called acknowledge that process ID 1338 has actually finished, and then as part of that, it can go back in waiting, and then the kernel can go ahead and delete that tab, so that process ID is now no longer valid. It wouldn't have an entry in that proc file system because now it can completely be deleted. And then Firefox would, go on, run at some point, and that's it. So we have to maintain this parent-child relationship. So previously, we kind of made sure that our parent exited last using sleep. So that's what that sleep was before. So I didn't get any weird ordering, but we don't need to do that. So I can't see images on that thing, so that's a rip. So previously we saw that our parent exited last using sleep. So let's see what happens when our parent exits first and no longer exists. So let's see, VM. So in our wait example here, let's make sure we can see it. So we have a fork, and then after the fork, we check the value returned. If it's -1, it means an error happened and our computer's probably dying. And then if it's 0, it's the child, so it can just sleep for 2 seconds. Let's go ahead and just say printf child done sleeping. And now, before we get into wait, let's just go ahead and in the parent, we'll just call this calling wait, and we'll just exit the parent. So now we would likely expect to see, whenever we run something, we would expect to see, it would start at main, fork, and then there'd be two processes, one going onto line 13 here, and one that wants to go to line 17 here. So line 13 is asleep for 2 seconds, which just puts that process to sleep. So likely my CPU is fast enough where this will happen within 2 seconds, and then exit. So returning from main is the same as exiting, so now my parent process is dead, and then after 2 seconds, my child goes ahead and prints a message. So let's go ahead and do that. So if I do that, what was it called? It was called wait example. So if I do that, I see calling wait, and then I can actually type on my terminal again, and then it kind of just interrupts me and throws the child done sleeping at me, even though I can start typing again. And that's because my shell here, it waits until the process it creates is done, and then as soon as it's done, it lets you type again. So it doesn't know about my child. So my child's still running whenever my process dies. So as far as the terminal knows, you're done running whatever you wanted to run. But then later on, after 2 seconds, it goes ahead and prints something. So any questions about that? Okay, so we are going to get into a way to prevent this from happening and make sure that all our processes finish before the main parent process dies. So I'll say a little bit more about, so the parent process is responsible for the child and only the direct parent process. So as part of the things you do when you terminate is you return, you call exit with that number, and that's called an exit status. So for example, whenever you call, if you return 0 from main, that's the same as exit 0. So that means the exit status of that process when it terminates is 0. If there's an error, typically it's just anything other than 0. So it'd be like 1 or something like that. So whatever you call exit in that child process or the parent process, it so far has, no one's read that exit status at all. So the minimum acknowledgement you can think of as just reading the child's exit status. So if you create a process and it finishes, at minimum, you should know what that returned, if it exited successfully or if it had an error of some sort. But there's two situations because that assumes that the parent always, the child process always dies first, but that doesn't have to be the case. So normally the child exits first, and if the child exits first, well, like I said, you can't delete all of that information until you acknowledge it. So the state that that child is in from the time it exits before it gets acknowledged, we'll have weird terminology here. It will only get worse as this course goes on. So it's called a zombie process. So it's terminated, it's dead, but it's still consuming resources. So that's where the name zombie comes from. So it's still consuming some resources on our system and we can't get rid of it yet. So that's why it's called zombie. And then the other name is if the parent exits first, so you create a child and then you perish or exit or die. They like using the term die, a little gruesome, but if the parent dies and the child is now parentless, so now it is called an orphan, very, very literal. And that is also something you need to handle as part of the operating system because only the direct parent can acknowledge the child. And now if the parent's dead, well, who's there to acknowledge the child? So we will discuss this through some more examples. So luckily, this name is about the only non-gruesome name we'll see. So that acknowledgement process I was talking about is called wait, and you need to call wait on a child process. So it has the following API. It takes an address to store the status of the process, and that is not just a number, it's coded, and you actually have to use macros to get some meaning out of it. And then Other things it does is it returns the process ID of whatever the child process is that is now exited that you've waited on, and it can now be cleaned up. So like all of these C wrapper functions, it returns -1 if there's a failure. It returns 0 for a non-blocking call with no child changes, and that might seem kind of like gibberish. All that means is by default, what wait does is it waits for a child to finish running. So if you call wait and nothing has finished running yet, it will sit there and you'll be in that block state where the kernel will not let your process run anymore until one of your children have actually exited. So so that's the blocking version. There's a non-blocking version you might want to use in this course, maybe not, that you can just ask straight away, hey, do I have any children that are dead? And then it can respond instantly, yes or no. So 0 is the no. If you don't specify that option, it just means that hey, it will block and wait for a child to finish. And then if it's greater than 0, you get the process ID of the child that had the change or the child that actually exited. So the wait status contains a bunch of information, and one of the things is the exit code, because calling exit is not the only way to end a process, but for the purposes of this course, it will be exiting and maybe one other way we'll talk about. But for now, you can just assume that processes exit by calling exit, or they get terminated by calling exit. So you need to use that, use our man pages if you want to use any of the other macros. And then wait will, like I said, wait for any child. And if you want to wait for a specific process to die, that is your direct children. So if you call this on something that's not your child, it will give you an error. But if you want to wait on a specific process, so say you created 8 children, if you wanted to wait on a specific one of them, you could use wait PID, which just takes another argument as with the process ID to wait for. So here's our simple wait example. It just starts with main, and like we've been doing so far, it calls fork. So now after the fork, we have 2 processes. The only difference between them is the return value of fork. One will be 0, that's the child that's newly created, and the parent will have the process ID of the child. So like I just showed in the child, instead of having that print statement, it just goes to sleep for 2 seconds. And I showed if there's a print statement after that, it kind of messes up our terminal, makes it look ugly. And then here's actually how you use wait. So it will say calling wait. It will create a variable on the stack, just an integer for something called W status, and that's the address that wait wants. So we call wait with the address of W status, and it will write some value to there that we can actually read, and it returns a process ID that we waited on. So hopefully it's the process we created, so it should match that process ID from fork in the parent, because we only created a single process here. So then we can use this macro here, this W if exited on the wait status. So that will just tell you 0 or 1, whether or not that process has exited. And for now, we can assume this will always be true for our purposes for now. And then if it's exited, you are allowed to use this W exit status macro that will give you the return value of that process, whatever it returned as part of exit. So in the parent, it would say wait return for an exit process, whatever that process ID was, and then whatever status it read. So let's go ahead and see that. So I'll just get rid of my print statements in this. So any questions before I run this thing? So if I run it, what should happen is nothing happens for like 2 seconds. I don't get control immediately from my terminal, because my parent process, the one that the shell actually executed, will go ahead and be calling wait, and it will wait for my one child to die, which will take 2 seconds, at least 2 seconds. And then after it returns from wait, it fills in that W status, so I can actually start using it and get some information out of it. So if I do that and I run my wait example, now I'm actually waiting for 2 seconds, and then it will finally return whenever my child is dead, and then say wait return for an exit process, gives me the process ID of the child, and then that status, whatever it exited with. So any questions about that? Yep.
What if you have multiple children?
Yeah, so if I have multiple children, then I need to call wait for as many children as I have.
Can you select the child?
Yep, so you can select a child with that wait PID one that I showed. Oops. Yeah, so there's this wait PID at the bottom. Sorry, there's another question. Yeah.
So what is the value of W status?
So the value of W status is something you're not supposed to read directly. You're supposed to access it through those macros. So it's supposed to be transparent. So instead of using W status directly, you should be using these like this W if exited thing. And if you look at like man wait, it tells you what all these are. So you're not supposed to actually know what the values mean in there. So instead of using W status directly, I use W if exited W status. And then if you read that, it says it will return 0 if it exited normally, 0 if it didn't exit, and 1 if it exited. And then I use W exit status here. And W exit status is whatever it returns. So if I do something like, so the usual convention is if it doesn't return 0, it exits. So in this case, I'll change it so that the child returns 2, and that would be thrown to exit. So my parent should be able to read that. So if I do that and I wait for it this time, then I see, hey, the status is different now. It's a 2 because my child returned a 2. And usually this would maybe change the behavior program if I know whatever I launched failed. Maybe I display an error to the user like, hey, your process failed or something like that. Yep.
In this code, where did the child exit?
So yeah, the question is where in this code did the child exit? And the child goes into here because it's the child. It sleeps for 2 seconds and then it returns 2. So a return, and it's in main. So return from main is the same as calling exit. And that's just the way C does things for you.
So before it returned 0 because we just skipped to the last line, which was return 0?
Yep.
Then status up to 0.
Yep. Yeah, it just went all the way to 0. If I didn't want to return from there, I could exit 3 or something like that, which should do the exact same thing. So if I exit 3, I didn't declare it, but whatever. Oh, it really, oh no, it's good. So I didn't declare it, but whatever, it still works. But I can also just call exit. Yep.
So if you had a bug in your child and it never actually returned, would there be like a timeout on wait, or would it just?
In which one? Like if the child just never exited? Yeah, if the child never exited, by default, that wait doesn't have a timeout. It's just going to wait as long as it takes. So if you want a timeout, you can do that yourself, and that would be through that like non-blocking call. Like you could just, hey, are you done yet? Hey, are you done yet? And you can not like maintain control. But by default, it's going to wait there forever. Yep. Yeah, so that's a good question. So the question is, what happens if I call wait without a child process? So let's just say instead of fork, I just go PID equals, I don't know, 2, 3. I just make up something. Whoops, I need to define it still. So if you call wait without a process, it gives you an error. So here, whenever I ran it, this, by default, your shell will actually tell you the exit status of whatever you just ran if it exits abnormally for some reason. So when I ran my process, it exited with this code 10. And if I go look at my code, please say I wrapped it properly. That here, I check wait, I get wait PID, and in this case, this is probably garbage and it didn't exit properly, so it went into this else statement and just returned and it got an error from wait. So it just hit that, exited with that. Child is just 10, so it died. Yep.
What is preventing the parent from exiting earlier than the child?
Yeah, so the question is, what's preventing the parent from exiting earlier than child? And the answer is nothing. And we'll see that. So if the parent exits first, that's that orphan case we have. So this is the case where everything is nice and proper. So let's go back. Oops. Okay, so this is our normal case where we actually properly wait for our children. We don't die first. Everything is well and good. So let's go into what happens when that is not the case. So the first one is that zombie case where maybe that child process is done, but the parent has not called wait on it yet. So it's just in that zombie state where it's still consuming some resources. So that means that child process is done, it's terminated, but it hasn't been acknowledged yet. No one called wait on it. And the process, might have an error. That child might indicate an error, but nothing ever reads from it. So it's like that tree falling in the forest kind of thing. They kind of plug your ears. So there's some things the operating system can do. So one of the things we'll see later in the course is the operating system kind of generates interrupts to processes. So one thing it can do is poke the process and say, hey, your child died. You should probably do something about this. But of course, because it's your program and you can do whatever you want, you're free to be like, yeah, sure, whatever, and carry on. So that's just a slight nudge where you don't have to handle it at all. So that's like the most basic thing. So that form of interrupts for processes are called signals. And by default, there's like some default handlers. The default handler for your child dying is to ignore it. Yep.
So just in the functional example that we just went over,
Yep.
what part is the actual acknowledgement?
Just the wait call.
Just calling wait is enough that it's acknowledged?
Yeah.
Once it should exit, it will just instantly exit because it's been wait has been called on?
So wait is the acknowledgement. So wait will wait for your child to actually exit.
So the parent will hang up at that line until the child is
Yep.
finished and then it will,
Yep.
and the child has been acknowledged.
Yep. Yep.
So when the parent process goes back into the ready state, it automatically makes the acknowledgement?
Yeah, so the acknowledgement is returning from that wait, and that process ID you get, that's what you acknowledged. Yep.
Can you wait for a process that isn't your child?
The question is, can you wait for a process that is not your child? And the answer to that is no. You get an error from the wait call, just like you would get an error if you tried to wait and you didn't have any children. So that's one of the error scenarios. So in this zombie scenario, the operating system has to keep that zombie process until it's acknowledged, like something has to read its exit status at the very minimum. And if the parent ignores it, well, that's the zombie that's the zombie process, and it needs to be waited to be reparented, and we'll see what that means in a second. But first, let's see that what a zombie process looks like. Zombie. Okay, so this example starts off kind of the same. Here, I'll make it a bit bigger. So it starts off kind of the same. We fork. So now we have two processes, and they're exact clones of each other, but so far nothing really interesting has happened. So one will have process ID 0, the other will have the process ID of the child. So in the child, we go ahead, all it does is sit here, wait for 2 seconds, and then eventually it's going to fall through here. Sorry I didn't show this earlier. Fall through here, and then after 2 seconds, it's going to return 0. So it's going to call exit, and it's going to be done. Then in the parent process, what we're going to do, we're going to just set up some temporary variable. to use for a return value. And then all it does is sleep for 1 second. So likely when it wakes back up, the child should still be alive and running because it just sleeps for 2 seconds and I wake up after 1 second. So I wrote a little thing that as part of you're doing for lab 1, so you're looking at that status file in proc and there's a bunch of information about it. One thing is its name that you're using. Another thing that's in there is its state. So in its state, you can read off what its state is, if it's running, if it's blocked, if it's whatever. And we can go ahead, read its state. So we'll read its state, print it out. And if we get some error from that, we'll just return what that error is. Hopefully it works. And then the parent's going to wait for an additional 2 seconds. So by this point, whenever it wakes up from this sleep, it would have been running for 3 seconds. And our child's dead after 2 seconds. So our child should be dead at this point. So it's dead, but it won't clean up any of its resources because we're the parent and we were bad parents. It's been dead for like a whole second, which is an eternity. And instead of acknowledging it, we'll just go ahead and poke its dead body and see what its process state is, just to show you that, you know, zombie states are an actual thing and I'm just not making it up. And all it does after that is it reads its state and then it just returns. So it never acknowledged the child whatsoever. It's just kind of in limbo. So if I go ahead and do that, so a zombie example. So I go ahead, so I see its state here, it's sleeping because I woke up after a second and then I go to sleep for 2 more seconds, it's dead, and then I can see that, hey, reading from that file, it's in this zombie state and the kernel actually tells you it's in that zombie state. So it means it's terminated, but no one's acknowledged it yet, and it's just kind of out chilling there. Yep. Yeah, so that's a good question. So we can see if the question is, hey, if that, you know, if the parent exits, does the OS finally clean up the resources associated with that? So let's go ahead and print out, whoops. So let's just print out the process ID of the child. So we can go ahead and poke around in that proc file system. So if we do that, okay, so my child is 41031. It was sleeping and now it's a zombie. Well, if it's still a zombie, it should have an entry in that proc file system because that just read it. So let's see if it's still a zombie and if it still exists. So it was 41031. So if I do that, it says no such file directory because it's got cleaned up by something, which is a bit of a mystery because I didn't acknowledge it. So if the rule is someone has to acknowledge it to be cleaned up, the natural question is, well, who did that? So that process, so that zombie process, whenever that parent exited, it became an orphan, right? Its parent is now dead, and it was also kind of dead, but no one acknowledged it. So it needs a new parent, and because it still needs a process to acknowledge it, that hasn't gone away. That's like an ironclad rule that will always be a thing. So what your kernel does is it does something called reparenting. So if the parent is dead, it will go through a process of reparenting. So by default, it will reparent that process back to init, which is process ID 1. So it will just be like, hey, init, you should acknowledge this thing, and that's one of the things init does. So now we know like the 2 things init is responsible for. So init is responsible for creating processes and also acknowledging all the dead zombies that come in, or everything that gets reparented to it. So you can kind of think of it as like the orphanage, if you want, as like what if you go through this terminology. So it kind of reparents it, and now init's now responsible for acknowledging the child. And you know, at this point, if init doesn't acknowledge the child, then you're just going to have wasted resources on your system, and they're never going to be cleaned up. So if you have a really bad init, then you're going to run out of memory on your machine faster. So hopefully someone good has written a init for you. So let's just create an orphan and see what happens. So in this example, I call fork again, and let's assume that there's no errors. So in the child, I just say, hey, who's my parent, which will be whatever just created it. And then after that, I sleep for 2 seconds, and then I'll say, hey, who's my parent now? And after 2 seconds, the original parent sleeps for 1 second, so it should be dead. So it should have went through this reparenting process, and that system call just tells you who your parent is. So if I go ahead and do that, so I say, it says, oh, child parent process ID is 41124, whatever, and then after 2 more seconds, I can see my parent's dead because I got control back on my terminal. And now it says the child's parent process ID after sleep is 701, which is not a init and not 1, which is kind of weird. But now we know, we can kind of figure out, well, what the hell is 701? So let's just go ahead and see. Whoops. 701 status. Oh, that's a great file. Sorry. So 701, we'll go through all this crap, and it's something called systemd, which I said was a init, usually what a init is. So this is actually systemd, but this is like the user version of systemd. So it's responsible for cleaning up your processes. So this is what some init systems can do, and by default, things will get reparented to init, but one thing you can do on Linux and other operating systems is you can essentially opt in to being the orphanage and saying, hey, if any of my grandchildren has to get reparented, instead of going to init, go to me instead and don't keep going up. So you can opt into this, and it's called being a sub-reaper, which is a very great name. So init is actually called a reaper as well, if you want to get into the terminology. So you can opt into being a sub-reaper, which means that, hey, I get to kill all the children, which is so fun, right? Yeah, terminology, real bad. Okay, so, but if you go ahead and run that example, so that will work on Mac OS or something like that. And on my Mac, like if I just run it directly, it gets reparented to process ID 1. So Mac follows the same rules, but uses a different init system. Yeah.
So I have a question. So if the child's processes exit first, and then like that's the condition for a zombie process to be created,
Yeah.
why are the zombie processes reparented?
So in this case, I kind of had a, so you can reparent a zombie or just a running process. So in this example, well, the child that had to get reparented was still running, so it was just a plain orphan process. And then the other example I had, like the first example, where my child died first and I didn't acknowledge it, well, before the parent process died, it was already a zombie. So it was already a zombie, and then the parent died, so it became simultaneously an orphan zombie, so it was both at the same time. So it was a zombie whose parent is dead, so that you can have both, they're not mutually exclusive. And then what would happen, that orphan zombie would get reparented to init, likely, or something else, and then it would get acknowledged and then cleaned up right away. So in this example, when it got reparented for the orphan example, it was already still running. Let me go back to it. So in this orphan example, when it got reparented, it was still running because it was still doing that sleep thing. So I was actually still running, so I printed out who my parent was. But when you get reparented, you could still be running, you could be a zombie, doesn't matter. All right, any more questions? Okay, if not, we see how well we understand things, and we go back. To reading something a bit more difficult. Oops. So close that. So let's go ahead and try and read this program. So, and we'll try and argue about what it does. So in this process, in this program, what's it do? So in main, it goes in this for loop, which starts at 1, goes to equal to 4. So through this for loop, I will be equal to 1, 2, 3, and 4. Hopefully everyone understands that right. Still C, everything still makes sense at this point. So it will call new process with I equal 1, 2, 3, and 4. So what do we do in new process? So a new process, it will fork. So this is a fork within a for loop. So it will fork, and then if PID is greater than 0, it will just return. So thankfully, in the parent, nothing that interesting happens. So in the parent, it will fork and then immediately return. So it just creates a process, returns. That's all it does. So in here, in the parent, it will just go through this for loop, and it will make 4 children. So, and then new process creates a child, returns, creates a child, returns. So hopefully that's okay. And then the more interesting case is what happens in the child. So it also checks if it's -1, just to error check, and my computer would probably be dying if that was true. So I go ahead and assume that that's true. And then now I'm in the child process. So each child will go ahead and print what its ID is, which is whatever, it's just a function parameter. It's I, and because they're exact copies at the time of the fork, well, first time through this, ID equals to 1. It forks. At that time of the fork, ID is 1, and the parent would return, and then the child, it would also have ID as 1. So it would come out here, and for the rest of that child, ID is always going to be 1 because it's a copy at the time of the fork. So it should print off process 1, and then this just prints off 10 times. So process 1, 0, 1, 2, all the way to 9, and then eventually it exits, and it takes a second to print each one. Now, when I call it with argument ID2, well, that happens another fork, and because 4 copies at the time of the fork, now the new process ID is equal to 2 because that's when it got created. So it would get ID 2, do the same thing, come into here, go into that for loop. So that process should print process 2 and then 0 to 9. And then similarly, the same thing would happen with 3 and 4, hopefully. So any questions about that before I run that? So what should I see? So I created 4 processes. I should see, hopefully, process 1, 2, 3, and 4, and they should all do like print 10 times. So let's go ahead and see just what happens. Whoops. So if I go ahead and do that, I see that, hey, it prints a lot of stuff, and it's not necessarily in any order because I created 4 children, and I just kind of let them go at it and see whatever happens, happens. So I don't know what order they print. All I know is within a process, it still makes sense because it's still executing instructions sequentially, more or less. So I'll see, process 1, I'll see process 1 print 8 and then 9 always, but I can't depend on any ordering between 2 processes. So let's just go ahead and verify that everything prints. So here we can just see what our luck was. So we created process 1 first, then 2, then 3, But when we executed it, well, process 3 printed 0 first, and then 2, and then 1. And then before process 4 even got to print anything, process 3 woke back up and printed 1. And then process 4 finally came in, printed 1, and then eventually we go through all the numbers. So every process will do the same thing in order between itself, but between all the processes, every time we execute it, we're going to get probably different orders. So this time we got 3, 2, 4, 1, 1, 4. Execute again, 3, 4, 1, 4, 3, 2. You've no idea what the order is, and it's always going to be different. Yep. Yeah, so the question is, why are they kind of ending at all the same time? And the answer to that is, is because I have this sleep, because I'm essentially making them fall asleep for a second each and then letting them all battle it out. So I can go ahead and just remove sleep. So likely that runs so fast that I might just see one process print everything it has. So if I go ahead and do that, so I see essentially process 1 here got kind of the short end of the stick. It printed 9 things, oddly not 0. And then process 2 printed, everything all in one big chunk together. So you can actually see when it kind of switches. So it got really unlucky. Process 1 started, printed off 0, and then the kernel was like, no, it's process 2's turn. And then it got chosen, and it went all the way until it finished, and then only process 1 went. And then process 3 went all the way to completion, process 4 all the way to completion. So likely printing something is really, really fast, and you get a fair amount of time whenever it chooses to switch to you, that likely you'll just print everything. But if we run it over and over again, we'll see that, not necessarily the case. So here, 3 got interrupted after it printed 0 and then 1, and then got interrupted before it got restarted again. But this is all some order that you can't really control if you just create everything and just say, hey, go for it. All right, any other questions before we wrap up? No? Good? Sweet. All right, just remember, pulling for you. We're all in this together.